Okay, recreational coding. I'm going to introduce myself when it fits the situation, so let's start. The whole thing started with this. My son brought this home from school, and this is, you don't need to read this, but I guess you can see what the task was. This was meant to be the exciting task at the end of the drill exercises, and it's actually a trap. It's just to try to be entertaining and just get more drill out of the kids. And so yeah, to make it more precise, that's a magic 3x3 square of integers where the rows and the columns and the diagonals all add up to 99. So it is actually a very simple exercise. So here is one: find the missing numbers, and it's very easy. Just give you a second to think about it, how to start. And of course you can figure out that, well, once you have two numbers, then you can easily figure out the third one. So that's not the difficulty. This is not exciting at all. So sure, and when this happened, I didn't care about it. That's not something I concern with. However, my son was very impressed with this one, and he wanted more, but there were no more. So he started to create his own. Okay, of course, as a young person, he didn't see that this is actually on a whole different level of difficulty. So sure, if you have a complete solution, a magic square, then you can create a puzzle by removing entries. But if you just start putting them in, well, then you have to backtrack often. So, well, you don't know whether you start with the good numbers or not. And then it's like, okay, well, the question is like, oh, how many solutions we have? How to get all the solutions? And then it's like, well, sort of get a limit on how many different puzzles we can make. So does this sound familiar? Numbers in a grid subject to some constraints. And yes, indeed, we have the Sudoku, which is, it's not exactly the same, but it's a very similar one. And it's and we have very nice solutions. So if you go to this very old book now, but it's still very good because our language is quite stable and the book is well written. So on the 16th chapter, you can read about logic programming, the core.logic library, and there are actually two solutions for the Sudoku. One is the just functional, and the other one is the logic programming. So sure, it's like if you see that there is an interesting problem and it's very similar to another problem you solved before or someone has solved before, it should be easy, right? So we can just modify the existing code. And it's like, okay, here's the complete view. You are not supposed to read this, but it's like, well, that's about it. And this code will find all the solutions and will answer many questions, and it will give us new questions. So yeah, let's try to look at it in pieces. So we want to have something like this. Okay, so I can print the original magic square. I use 0 where we don't know. Okay, so that's the sort of the internal representation, and whenever we have a number, it's sort of the hint, we just have the number. So this was the original puzzle, and we want to do something like this, that we give the hint and we want to get the solution back. Well, sure, in this case we only have a single solution as expected, because it's in order to solve this puzzle, you don't need to do any real computation, in a sense that there are no conditional statement, no branching, just mechanical finding the numbers. So yeah, this is what we want to have. And just as with the Sudoku, since we have a very plain representation, just a vector of the 9 numbers here, we have to have some very straightforward functions to put the views on it, to sort of chop it up as we want. So MSQ is the magic square, and if we want to have the rows, well, we just partition every 3 elements, and well, once we did that, it's super easy to get the columns as well, and it's like there's a bit to get the diagonals. This is not as elegant code, but well, yeah, that's what it does. So we have the rows, the columns, and the two diagonals, because later we are going to use these. So that's okay. That's just boring technical bits. Let's look at the main part, and so yeah, that's how you use the logic engine. So that's the big thing about the logic programming, that the actual job will be done by the inference engine. So, well, that's the declarative idea. We just tell what we want, how the solution looks like, and then the engine will figure out what to do in order to get the solutions. So the first thing I want to mention here, that is like, okay, we want to restrict our universe. When it's like where this problem lives, we only have these 99 numbers from 1 to 99, because the logic engine could take this as very open-ended, saying that, well, it's like, if there is an empty cell, what can I put there? Can I put an elephant there? Can I put pizza there? But no, we just want to have the 99 numbers. So that's why we define the legal numbers. Then we have the logic variables, and it's like, did I just say variables? Yes, indeed. So we have variables here. The idea in the background, the logic engine will systematically assign values and reassign values to these variables. But it's like we don't need to worry about it, because that's that happens behind the scenes. But so variables, that's sort of a justified use here. So now, of course, I have these 9 logic variables, and I have to do this spatial separations, get the rows, get the columns, and the 2 diagonals. And I just put these together, and I just call them tuples. It's like all the triplets, so to speak. And now these are these are the logic variables. So that's the setup, and this is how you use the logic engine. You say that, well, you do the logic run star, which means that, okay, do not stop after the first solution. Let's just get all, and our Q will be the query variable. That's where we get the solution back in. So what do we see here? Well, it's we need to bind all the hints. Okay, so it's like if there are numbers already in the square, well, we want to fix them, and we just want to find the rest. So I will talk about how this happens. And then we have 2 other conditions here, that it's like every logic variable should be in the set of these, in the domain, a finite domain of these legal numbers. And here's the other one, is that the sum for all tuples should be 99. I will talk about Sumo, because it's such an interesting name for a function. Okay, so here we just gave the properties we want. So let's look at how to include the hints. To be honest, this was the part that took me the longest time to understand, and it may help some others. So the idea is that, well, if you know some numbers, you want to put them and tell the logic engine that, well, okay, those are fixed. So this is how you do that. If you have the logic variable and you have the actual hint, if the hint is 0, that means that we actually don't have a number. Then you put logic succeed, which means that it's like, okay, it's fine. The engine succeeded, and this took me a long time to understand. Okay, look at the other case. So in case you have a hint, you unify. So it's like, well, you sort of bind it to the logic variable. But why do you say succeed in the other case? Well, because this is just part of the story, and there will be other constraints in order to find that. Here you just need a placeholder for that. So that's why it's like, in this condition to be satisfied, it's all good. Other conditions will take care of that. And of course, we want to go through all the 9 entries in the input and bind the logic variable if we have an available hint. Okay, here is Sumo. So there is this tradition in logic programming that if you write basically a goal or a condition to be satisfied, you just put an O at the end of it, and it's an interesting tradition. It leads to interesting names. So here, like Sumo, and that's okay. So this goal succeeds if adding up the elements of L is actually the given sum. So yeah, let's think about this, because that's the crucial bit. This is the difference from vanilla functional programming and logic programming. So that's relational thinking. So what's that? If you have functional thinking, well, you have a function like, okay, here in a numerical one, it's just 2 to the power x. So you have the input and you have the output. So f of 3, and that's 2 to the power 3. That's 8. Okay, so you have the input and you have the output. And well, okay, you can think about a very much related function, and that's the base 2 logarithm. If you ask, well, what's the input here is 8, and what's the output? That's 3. Okay, so that's functional thinking. It's like you have an input and you produce some output. In relational thinking, there is no input, there is no output. You just have 3 numbers in a relationship. You have 2, 3, and 8, and they have this very special relationship, which of course, and I mean, for practical use, we have the exponential function and we have the logarithmic function. And for the third one, it's like we actually don't have a practical function. It's like I give you a number and another one, then it's like figure out in what base this would be the logarithm of that. Okay, but the point is that in relational thinking, you don't have input and output. You just state what's happening. So here, what we are saying as the input for this function, which represents a goal, we give a list of numbers and we give the sum. Okay, and the goal succeeds if that's the case. Or look at here, this one, as like the cons becomes conso, and it says, instead of just having the cons head tail, we have also the result as well. Okay, because the consync relationship has 3 things: the head, the tail, and the list itself. So we are not producing the output, we are stating the relationship. So this is how, well, otherwise it's recursive, and it's like fairly standard how to check the sum is actually the sum of the element. Okay, I think this is the most important part here, as difference between the functional and relational thinking. Okay, all solutions, how many do you expect? So now it's like I'm not giving any hint, all the holes are empty, and now the engine will go through and find all possible solutions, all magic squares for this condition. So think about it. I asked several people, and I get quite a diverse range of predictions. Someone said, there are only a few because it's anyway constrained. Others would say that there are very many. Then realizing, we don't have negative numbers. So yeah, sure, we don't have infinitely many, but maybe still there are many. Okay, now as you thought about it, we have 2113. This is of course not the most clever way of doing it, because while some of them are symmetric, so it's like the actual number could be should be lower than that. But it's like, okay, here's some statistics. Once you can have the solutions, well, you can easily figure out, it's like, oh, how do they look like? There is one solution which uses only one number. So here I'm looking at the final solutions and just count how many different numbers we have in them. And it's well, most of them you have 9 different numbers, but there is one which has only one number, and that's probably not too difficult to figure out. That's the one when you have 33, 33, 33. Okay, so yeah, that's fairly interesting. But of course, if you have answers, then you have more questions, and questions lead to other questions. So let's say it's like you ask that, oh, can I put 1 and 2 in the first 2 cells and then find a solution? No. Okay, so it's like, well, if my son did this, putting 1 and 2, then it's like there is no chance. And if you do it manually, of course, there is no way to see it until the very end, and then you need to backtrack. But if you just put 1, well, you have one solution. So this would work. And it's like if you put 11, well, you have more. It didn't even fit the screen. But the question is, do you see something interesting here? And I guess, yeah, you can see the pattern. It's 33 is in the middle. And well, you can check it in the REPL very quickly that, yes, that's the only number we find in the center. Okay, so that's interesting. And it's like, okay, now I can introduce myself. So I teach mathematics and programming at Akita International University, and I often do sort of problem solving sessions, both for programming and for good old mathematical problem solving. And now this question was like, okay, this is actually something that I can ask. Can you prove that 33 is always in the center for this one? And it's like it's actually it's very simple. So I tried it myself, although usually I do not solve the problems myself, and I ask the students, because then I have a sort of an unfair advantage. So I prefer just working together. But this one I checked, and it's surprisingly quickly you can find the answer that, okay, as like computer says that there is only 33 there. So there should be a way that mathematically we can show this. And it's very simple. You write down all the triplets that has the center in it, which happens to be E here. Then you rearrange them. And then, of course, you see that A plus B plus C, that's also 99. So you write them down. And again, it's a bit of rearranging. You get 3 times E is 99 and E is 33. So yeah, okay, well, that's the job done. We had fun with this one. And so this worked out quite nicely. So I thought that, okay, here's another problem that I had with the kids. There is this ancient game, snakes or chutes and ladders. And the idea is that, well, you need to reach the goal, and if you are at the bottom of the ladder, you can climb up. And usually there is a moral story behind it. So if you do something nice, then you can climb up the ladder. But if you do something naughty, then you fall down and you slide down on snakes or the chutes. So this is a very classic game. The only problem that I really don't like it. So it's like, I mean, you know, I like games like Go, where you have to think, and here it's like it's all random. So I always wondered, when we play this game, because the kids love it, it's like, how long will it take? So what's the expected number of rolling the die before we finish the game? So it's like, okay, let's calculate this. Of course, I simplified it, And I knew what's the proper mathematics behind it, because well, there is this Markov chain and this like matrices, whatever. But why would you do it in the proper way if you can have a lot more fun in the sort of in the hard way? So what I want to calculate here, what we wanted to calculate here is that how long does it take on average from each square to reach the finish? And of course, if you are on square 9 and you have the standard 6-sided die, then it's like it takes one move, because no matter what you roll, you will be there. But from 8, now that's okay. That's a bit more complicated, because well, it's like you can roll 1. What's the probability of that? You're rolling 1, and then I was like, well, then with that probability you will have 2 turns. But you see, what complicates is that you have these loops. Okay, so what we thought, it's like when we started to calculate, wow, okay, sure, infinity is involved, so there are infinitely many, so probably we will not be able to compute this. But let's see where the difficulty comes up. So we did many calculations. This is just a shortcut of that, and we had many different results, including so of course, I mean, when humans do this type of calculations and it's not a textbook example, it gets complicated, then we of course make mistakes, then it doesn't make sense. And it's fun to watch people, including myself, as trying to rationalize the obviously wrong result. But okay, anyway, we had fun, and we got to a point where it's like we realized that, oh, this is actually, you can actually calculate this. There is no infinity involved. It's just a bunch of it's a system of linear equations, and that, of course, that does make sense, because well, that's what the matrix multiplication is about in Markov chains. But okay, to cut it short, so we were never happy about the result, and we were not sure, so that was another REPL experiment needed. Okay, so I did something very quickly, and this is, you know, it's not production code or anything. Just put this together in the REPL and then put it on the other side, on the other window, and it's like, this is the code. This just simulates. This is not even a function, because it gives you different answer each time, because it has rand int in there. Well, what I did, I actually simulated all these. Well, it's like how many times? It's like 1 million times. Okay, so we have this process, and it's like this is hard-coded the structure for that one, and when we finish, well, we don't give a number anymore, which is this function will give you that what's the next square you land on if you roll a die. And then, well, okay, we just calculated these probabilities, and at the end we realized that, okay, we were calculating it correctly. It's just, well, at some point we made an error, and that's why we had this problem. Again, it's a lot of fun. So then after this we had another problem, but yeah, that one I will talk about it next time. So, well, tea time. Thank you very much.